But we don't only want to make this available for very technologically advanced users. We know that people today have become very accustomed to mapping you see on your phone and on the internet, where you don't need any special skills. You just go there and click a button and zoom in and pan around. You can find exactly what you want. So we're also building a set of interfaces that mimic that experience. This is an early example. It's planet.com/mosaics. If you talk to Ed at MapPoint Asia, he can help you get access to this so you can have a look around. But basically, it takes all the imagery we're capturing and color corrects everything so it looks consistent and places it onto a map. And then when you come and look around, you can zoom into Thailand and click on a specific place, and it will immediately show you all of the images that are accessible, and you can click and download them. So we have a mosaic browsing experience and also a scene browsing experience. And so this experience allows you to take a lot of the filters that I previously described and just move some sliders across. So how high do you want the satellite to be flying when it took the image? What is the angle of the image that is acceptable for your use case? And how good is the image? This is using a technique called signal-to-noise to measure that. So this is a key part of what we're doing. We're not only capturing huge volumes of imagery very quickly, but we're making it easily accessible. And we believe we are at the cutting edge of web-based mapping tools and making it accessible. And we would be excited for you guys to try that out in the break, or fingers crossed form kind of longer-term partnerships with us to work out how to use this for your issues.
Yeah, just to re-emphasize what Alex is showing. So this is not any special software. This is operating in a web browser. Again, we'll demonstrate this after the break, but you can interact with our data, even data that's been collected within the last 24 hours, you'll be able to have access through your web browser. So that, again, that's not something that exists in the market today, and this access not only is relatively open, but it's also universal. So through our partnership with MapPoint Asia, they have access to all of the data that we're collecting in Thailand now and through the next couple of years. So again, any information at any time can be readily accessible in the most simple way that most people are familiar with in terms of web browsing.
But these are great questions. Anybody have any more?
ท่านใดมีคำถามเพิ่มไหมคะ
One at the back.
Thank you and good morning. First of all, I think sample images is quite impressive, by the way,
Thank you.
in terms of visualizations. However, I would like to know or learn more about the specification, like resolutions and spectral bands. What's the spectral band of your DOF, I mean satellite?
Sure.
And second question, it seems like your sample, your images is not capturing in rectangle, right? But rather be round. Why would you decide the images like that? Just please share.
Sure, of course. No, and I appreciate that because I too was a bit confused the first time I saw some of this imagery. It was round versus square. Most of us are used to square imagery. I'll answer that question first. So as Alex was showing the satellite, you can see that it is quite small, and we basically want to maximize the amount of data that we capture. So the telescope is round. With the early design of the telescope, you can see on this image here, some of the corners of the image are effectively obscured simply because we have such a small aperture. That is one of the reasons why we have designed a new telescope to go into the satellite that will enable us to use the entire frame. So a lot of the imagery that we will begin collecting this year, we already have a couple of these satellites in space, will start to look more familiar to users of satellite imagery, meaning it will be a rectangle. It will use all of the data that's collected on the back of the CCD or the digital camera, which is a rectangle.
And I've just one more thing to add. I was actually talking to Chris Bosch, who's our CTO, about this exact question. And he was telling me that when we design a satellite like this, we want to future-proof it. So we purposefully put in place a sensor that was actually too big for the optical unit, knowing that we were going to make advances like the ones I described. So what that means is the sensor is bigger than the amount of light hitting the CCD, so there just was less light hitting the corners. A lot of people would try and not deliver that to customers, but we kind of believe there's value in every pixel, no matter how high quality or low quality that pixel is. Someone will probably find use for it. So instead of like not showing that to people, we chose to show it to people. We think it helps them understand kind of how this all works. And it also allows us to, in the future, put in place better telescopes, which will produce pictures more like the one you're seeing here. So a lot of the imagery in the browsing tool is basically kind of imagery we've collected over the last 12 months. And so you'll see it change over time as we get better at taking pictures and produce higher quality pictures.
Yes, and to answer your question about spatial and spectral resolution, so right now we have our satellites operating in a couple of different orbits. We have a lower orbit for satellites that are launched to be delivered to the ISS as effectively cargo. So as the astronauts on the ISS receive their food and their science experiments, there are boxes that we can put on these launches as secondary cargo that get loaded into the ISS. After they have been on the ISS for a few weeks, they deploy those satellites in space. Some of the pictures that we showed you are those satellites coming out of the ISS. That orbit is about 400 kilometers above Earth. That enables us, with this form factor of satellite, to collect at a 3-meter ground sample distance. We also have satellites in a higher orbit, in a sun-synchronous orbit, which is more traditional for Earth observation satellites. We wanted to test this orbit with our satellites as quickly as we could. Last June, we were able to get 12 of these satellites into the sun-synchronous orbit that is about 580 kilometers, so about 180 kilometers higher in space than some of the ones that you've seen here. Those produce data that is a 5-meter ground sample distance. Going forward, as Alex mentioned, we're always refining our satellite design. Now that we have a mature satellite design and a very advanced telescope design, we will begin launching satellites into our ideal orbit, which is anywhere from 425 to 475 kilometers above the atmosphere in sun-synchronous orbit. So that basically means that the sun angle is always the same every time we pass over the same spot on the ground. Those satellites will be able to collect at a 3-meter ground sample distance. So if you look at some of the early sample data, you'll see some 3-meter, some 5-meter, but the large majority of data that we'll be collecting over the course of this year and into the future will be 3-meter data. Currently, the satellites have a visible spectrum camera, meaning they have red, green, and blue bands. Those bands match very closely to what you see on the visible spectrum in satellites like a Landsat or something like that. We're also currently experimenting in space with a near-infrared sensor. What that will do, of course, for those of you who have mapped forestry or looked at agriculture data through remote sensing imagery, you know that near-infrared enables you to measure chlorophyll content, or basically the vigor at which a plant or a tree is growing. So that will come online later this year, and then effectively going forward we'll have visible spectrum plus near-infrared spectra available as our data source. Did that answer your question? Okay.
ท่านใดมีคำถามเพิ่มเติมไหมคะ Well, I have a question.
All right.
Please.
Right, because you said you have built 28 satellites and put them up together. So my question would be, what's the main difference between each 28 satellite?
Sure. So with every launch, we do a couple of things. The first is put up the current stable design that we are completely 100% comfortable with, that we know is going to work and produce great imagery. So that's often like the bulk of the launch. But because we're launching so many, we can't resist the desire to experiment. So the remaining units are often various experiments we want to try out. So we may want to upgrade the power system. We may want to upgrade the circuitry or the memory. We may want to try a completely new telescope to see how that functions. And not just how that functions on the ground, but how that functions in a space environment. So we always reserve a few spots for technology demonstrations our technical team is excited about, and things that can dramatically push forward what we are capable of doing. So yeah, those two pieces, a stable satellite and experiments.
And I also heard the question from the back. He asked, for the old version of your satellite, is there any particular one that you bring back to use it again, the old version?
Yeah, unfortunately, once the satellites are in space, most of the time they're stuck in